Could you tell us in a few simple words the highlights of your talk, please?
So, okay, the goal of my talk was kind of summarize the status of the field and some recent developments. There are three things which I wanted to stress. One is the status of really minimal thing which we know, standard model plus neutrino mass. Not even right-handed neutrino or something like this, existence of this, but just mass. And the main message is that this kind of framework is in very good shape, with very good support from the experiment and recent data. Now, I also discussed anomalies, which actually were a driving force in development of this field. And it seems that anomalies are losing sigmas, so which means that everything is kind of move to settle down without any anomalies. It's a good support of everything.
Which is nice. Yeah. I like that.
Well, this is a matter of test, because then if there is no anomalies, then what to do? The question. So
I think the standard model should be the standard model, and then we look for more imaginative stuff.
Well, this is we are working on extensions of the standard model. The standard model is 40 years old kind of subject, and so the same fight is for sterile neutrinos. My point is that the case of existence of sterile neutrinos, which is a very active field now, becomes weaker and weaker.
Maybe you explain what is sterile neutrinos, because.
So this is one of the extensions of the standard model, and sterile neutrinos are neutrino states which have no usual weak interactions, and there are few anomalies which testify to some extent for existence of these sterile neutrinos, like old LSND, then mini Boone anomaly, then a set of reactor experiments. And it seems that at least anomalies which are showed by reactor experiments, it seems they simply disappear. Still, there is a kind of question about mini Boone, but it seems these are not oscillations and not, say, electron-volt scale sterile neutrinos. So we were always worried about some desert at high energy scales, above electroweak scale, but now. So we have new trends, and people start to explore another desert, which is below electroweak scale, and we have 40 orders of magnitude, say from electroweak scale down to the scale determined by essentially the size of the universe, which is kind of probably the smallest scale we have. And in recent years, there are very active work on developments of new physics at low energy scales. And neutrinos are kind of in intermediate ranges. It belongs to some extent to this very low energy scale. Their masses are below 1 electron volt. And now there are plenty of developments related to, say, axions, axion-like particles, attempts to explain dark energy and dark matter at these low scales. And so I discussed a possibility that neutrinos are somehow communicate to these very low energy scales. And there is a rich phenomenology which is not completely elaborated. And in the case of neutrinos, you may expect some new refraction effects, for instance, or even a possibility to substitute neutrino mass by effective mass, which originates from interactions with this light sector. And one can again discuss bound states of neutrino composite systems like neutrino stars and clouds. So that's you get for free. That's what I have discussed actually.
The next question is from the experience you have from these days, and given, now we started to renovate these buildings in the prospect to make an institute that you could come and work here and so on. And what is your impression of what we are doing here?
I'm here just for 3 days, and actually I was just once at the Corfu conference, but it was a long time ago, and maybe not even in this place, right?
Yeah, could be in some. I thought that this was your first time, but apparently people told me that they remember you.
I was
Of
once,
course,
yeah.
I know. You.
I even don't remember when it was.
I see.
So I think it's a great pleasure to be here, and so the hall is very nice, and
We have several young people around, as you noticed, and what you will suggest to these young people? I mean, these are young people who start research more or less. They are doctoral level, maybe few at master or postdocs. Is it worth continuing? Is exciting our stuff?
look, I probably will disappoint you because my kind of point of view that young people know better what to do than we are. No,
Yes.
this is also my experience. I remember when I was young and started to do, I have my idea what I should do, and I was thinking, okay, these old people are, doing the same thing. So even now I'm asking young people, so what do you think is interesting? Because they have, to some extent, I think, better feeling. There's and so the only my advice that they should start already to think seriously what is important and not just follow what supervisor is saying.
Or fashion or something.
Otherwise, there is no development. They should know what is important better than we.
Thanks a lot for organizers for the invitation, and it's really great their kind of courageous step to organize something in these difficult times. So I will talk on neutrino physics in the COVID era. This is the outline. First, neutrinos in the standard model plus mass of neutrino. Then neutrinos and beyond the standard model. I will discuss anomalies and connections and possible inference of these. Then I will focus on neutrinos and new physics at the low energy scales, kind of the area of active research in the last years. And then I will comment on masses mixing and flavor symmetries, trying to have some assessment of the present day situation. Massive neutrinos and the standard model. So this is what we know. We know that we have very well tested standard model plus mass of neutrino. I'm not saying left, right neutrinos, or just mass of neutrinos, which actually were obtained through oscillations and adiabatic conversion in different experiments. Important point is that new physics beyond the neutrino mass can be actually introduced in such a way that the feedback of this new physics onto standard model is very weak, so that we are just left with neutrino masses, not even knowing what is the nature of neutrino mass. And actually, there are several possibilities that can be Dirac neutrino mass. It can be Majorana, for instance, through D5 Weinberg operator. But it can be effective mass, which is generated by interactions of neutrinos with medium, for instance, with dark matter. And I will comment on this later. So this is the summary of analysis of all experimental data. This is a recent paper. And a few things to mark. One is that normal ordering is somehow 2.5 sigma is preferable. So red is inverted and this is normal. Now, we have CP phase, which is now closer to pi, and deviation of 2-3 mixing from pi over 4 is smaller. So all the things will have some impact on the future studies. One should mention that the data become more consistent, analysis stable, and this group gives results which are quite similar to what a new fit, another group, is giving. So the data agree actually with hard mass and no dependence of mass on energy, environment, it has been observed, which is very important. Actually, test to understand what is the nature of neutrino mass. The question is if there is any tension inside this global field. There are two things quite recent. One is that so-called solar Kamland delta m squared to 1 square tension disappears. The recent results from Super Kamiokande and also SNO plus now observe some distortion of the spectrum of events, which actually is consistent with what is expected. And then day-night asymmetry at Super Kamiokande is reduced from 3.3 to 2.1%. That leads to the shift of the best fit of delta m square from solar neutrino data to upper values. So it's like shift like this. And now kind of difference of the solar neutrino and Kamland is something like 1 sigma. So that essentially anomaly disappeared. Now, neutrino anomalies, and I will discuss some anomalies and their status. One is the reactor neutrino anomaly, which actually states that the present day observations made at different baselines distance is these rates are smaller than what is expected according to Huber-Muller predictions, which are based on Grenoble spectra. So Grenoble actually measured the energy spectrum of electrons of different isotopes, and especially uranium and plutonium, and they converted this energy spectrum of electron to energy spectrum of neutrino. So recently, it was some measurement in Kurchatov Institute of this ratio of uranium to plutonium, which is important ingredient in these computations. And what they have found that the measured ratio is below of what Grenoble experiment did. And so this means that if this result is correct, that just anomaly is absent, because it's, this ratio for Grenoble is I think it's opposite, right? So this R for Kurchatov Institute is smaller, and this precisely, almost precisely, reproduces the observed ratio. So new measurements actually, they reduce the expected flux, and therefore anomaly disappears. Now, there are several experiments indicating different, neutrino oscillations, and in particular, it was NEOS experiment and DANS experiment, which last year actually indicated the same delta m square, which was interesting, and some people became excited. Or it's not just one experiment indicates some delta m square oscillations with certain delta m square, but two experiments. And things changed because NEOS did a new analysis, and now they have delta m square 2.37 electron volts, while DANS experiment, this Russian experiment, gives 1.3. So it's like, the question is, do you have what? Do you have oscillations or fluctuations? And what is important, that oscillatory curve with two free parameters, delta m square and mixing angle, always gives better fit than just constant. So they reproduce better the fluctuations. So it seems there is nothing here. And I will not comment on neutrino 4, even Albert did want to comment. This is something which actually contradicts to everything. Neutrino and other anomalies. There's big activity in studies of neutrinos and dark matter. And there are different ways how neutrinos can be connected to dark matter. So right-handed neutrinos themselves can be the dark matter particles. Or so dark matter particles can participate in generation of neutrino mass. The same symmetry can be responsible for smallness of neutrino mass and stability of the dark matter. And what I will discuss a little bit is that refraction on the dark matter can produce effective mass of neutrino. Now, there are other connections, mass of neutrino with G-2 or the B anomalies, and so there's plenty of papers studying this possible connection. And the game is to use, of course, effective field theory and proceed in the following way. You first write all possible, say, operators constructed out of particles of the standard model, which violate a lepton number by 2 units if you want to produce a Majorana mass of neutrino. Then if you closure these lines, like for instance here, with 2 Higgs here, fields, this is precisely D5 operator, which generates neutrino mass. Or you can move in opposite direction. You can open this box or this circle and to see which kind of interactions are normalizable you can introduce to reproduce this operator. So this gives you new interactions and new particles, which can actually contribute to these anomalies RK, RD, G-2, and simultaneously give you the completion of your operator of generation of neutrino mass. So now it's machinery. It's really no need even to have kind of artificial intellect to do this job. So I don't think that this is what I'm saying, but now we can do model building without model builders. So there are programs which actually produce for you all this, realize this program, and you get finally which particles you need, which masses, etc. Now, neutrino physics and low energy scales. So all these years we worried about some high energy scale desert, which is something like 14 orders of magnitude here. So this is mass scale. This is the scale around 1 GeV, where our particles are living, the standard model. So we were worried, so what happens here? And just ignored, say, 40 orders of magnitude desert below the standard model scale. So what we have here, what we know is 1 over a lifetime of the universe, then the bound on the rate of proton decay, which is somewhere here, possible bound on the mass of the photon. That's it. So now we started to populate this area with various things like axion-like particles, like dark photons, etc., etc. Well, the question is, of course, there's some hierarchy problem here. So how about hierarchy problem in this case? What is interesting that we play, what is important, that we play here with very small couplings when we go to small scales, and that actually saves us from various problems. So that's a general scheme we are working. We have standard model, we have probably neutrino portal, Higgs portal, and then a lot of stuff here in the dark sector. Well, actually, neutrinos probably provide the link because their scale is somewhere in between the standard model scale and something what happens below. Let me just show what's going on in the very simple example. And so let's take just interaction of a neutrino with some new fermion, which could be right-handed component, and the scalar field. Actually, that started already a long time ago to trying to extract some information from this type of the interactions. So G is effective coupling, and there is quite stringent phenomenological bound that G is smaller than 10 to minus 7. And this type of the interaction, because this is doublet, the charge on here are singlets, this fermion and F, so that can appear through the right-handed neutrino portal. What we are saying, so through right-handed neutrinos, you can introduce such an interaction with small couplings. It's interesting, it's simple, but it has a very rich phenomenology for light particles. So we can have new effects in refraction. And what is important that this effect is actually proportional to G squared over the mass of mediator squared. And therefore, when you reduce G squared and mediator, this effect doesn't disappear. So that can actually generate effective mass of neutrino. Or with this, we can even produce bound neutrino system, like bound stars, clouds, etc. So this is the last part. And actually, Joe Pineda helped me a lot. So I just dropped many slides, and this is why I managed to finish today. It's a nice introduction to the topic. And you see here many authors which contributed, and I could probably fill in all this slide with authors who are actually doing these things. So this idea to use modular symmetries as flavor symmetries are motivated by string theory, actually these modular symmetries, and the hope was to reduce the number of parameters to make things more predictive and connect masses and mixing. Well, actually, let me make one comment. So our previous approach was precisely to decouple masses and mixing, because it was clear from the beginning that it's difficult to explain this larger, almost say, double maximum mixing in lepton sector with mass hierarchies. And it was very interesting, actually, an unexpected result that you really can decouple masses and mixing. Of course, you can construct flavor models where these things are connected, but this residual symmetry approach precisely aimed at a different explanation of mass hierarchies and mixing. So this is one of the examples of this type. We have, say, SO10, and so we have this usual nice stuff. And we introduce 16-plet, which actually provides a connection between visible sector and the dark sector. And it is in this sector we have, say, S4 symmetry. I have here flavons or something else if you want. And it is this which produces for you bimaximal mixing. And then you can reproduce the experimental data. And it is my conclusion. Thank you. So it seems that three neutrino framework works well, fine. So anomalies and tensions are losing their sigmas. And now I don't know what is the anomaly in neutrino physics. So in particular, the case of sterile neutrino become weaker and weaker. So neutrino interaction with light dark sector has a rich phenomenology. It produces so-called resonance refraction at low energies, a possibility to substitute or maybe partially substitute usual neutrino mass by interaction with medium. You may probably explain some features using this additional contribution. And one should worry, actually don't forget, once you introduce this, you will get these bound neutrino states. The question is, what are the properties of these bound neutrino states? Well, number of neutrinos here is 10 to the 22, 10 to the 25, 10 to the 40, maybe. It depends on the parameters. So, but one should actually check and maybe get even additional bounds or observe something interesting. And then modular symmetries, I don't want to repeat again, is promising. And I think, so we are still in exploratory space. But one should also keep in mind that maybe we apply them in not quite right way. Thank you.
So, Professor Valle, tell us, briefly explain to us the main subjects of your talk.
Okay, my subject was theory and interpretation of neutrino data. Neutrinos are tiny particles produced in the Big Bang in nuclear fusion reactions that take place inside the sun, also in supernova explosions and in cosmic rays and so on. They are also produced artificially, for example, in nuclear reactors, particle accelerators, and so on. And these are used to study their properties. So in my talk, what I did was to describe how to use neutrinos as guiding posts to solve the big problems of particle physics today, and to gain a better understanding of the universe. For example, neutrinos could hold the key to the understanding of dark matter in the universe. So they might explain why we have exactly 3 families of fundamental constituents, and so on. So this basically is a summary of what I discussed.
Okay, so do you have previous experience regarding the Corfu Summer Institute? And tell us some words about the workshop.
For sure, I have been in Corfu many times before. In fact, since the last millennium, I started going to Corfu, and it is a well-known school for the training of young scientists, and it offers very good courses and also a fantastic environment to do physics.
Okay, and what's your suggestion to young science students starting to be engaged in research?
My advice is always follow your heart. If you like physics, you should go ahead. Although a PhD in physics does not ensure that you have an academic job, the skills that you learn, basically how to think critically, these are always useful. And also the techniques such as math, computer software, statistics, all of these can be very useful in domains that can be very, very diverse, such as aeronautics, big data, clean energy, economy, medical physics, software development, science, education, and communication. And in fact, from our own experience, our group performing many scientists that have developed their careers both inside Europe and also outside Europe. Many of them have followed the jobs in the private sector in all of these areas that I mentioned. So a PhD in physics is not definitely a dead end.
Thank you very much. Thank you.
Okay, so first of all, I wish to thank the organizers for their kind invitation. It's a pity not to be present, but we are in pandemia. So my task is to illustrate to you the role neutrinos can play in helping us to make the first next step forward in particle physics. I start from neutrino oscillations. The discovery was made in solar and atmospheric neutrino experiments. These have been followed by reactor and accelerator-based studies, which have not only confirmed the oscillation phenomenon, but also improved parameter determination. So much so that, in fact, we now have a quite consistent global picture with a good determination of the lepton mixing parameters. These are the leptonic analogs of the CKM matrix elements characterizing the quark-weak interactions. Except for 3 points, namely, we still lack a good determination of the atmospheric octant, of the CP phase, and of the ordering of the neutrino spectrum. You see, you have two solutions for normal and inverted ordering. Instead, I will jump to neutrinoless double beta decay. First, this process is very important because it is associated to the Majorana nature of neutrinos, and it offers the possibility to probe parameters that are inaccessible to oscillations, such as the absolute neutrino mass scale. You see here, indeed, you have the 3 mass eigenvalues present in this amplitude, and also the 2 Majorana phases, which are characteristic of Majorana neutrinos. And notice that I'm using here our original parameterization of 1980, because it is much neater for the description of neutrinoless double beta decay, much neater than the choice made by the PDG. The most favorable situation for having a measurable neutrinoless double beta decay would happen if all neutrinos are nearly degenerate or are degenerate. And to describe this situation, I give you a novel description of these M beta beta parameter. Instead of plotting it versus the lightest neutrino mass, I express it in terms of this degeneracy parameter eta, a dimensionless parameter, so that when it equals 1, neutrinos are strictly degenerate. In real life, this is just an idealized limit. One must depart either to the left, that's the normal ordering band, or to the right, the inverted ordering band. Experimentally, we have already the brown band ruled out by the Kamlan-Zen measurement. And in the recent study with these people, we have analyzed the cosmological restrictions, which basically rule out the vertical band that you see here. So altogether, quasi-degeneracy is strongly disfavored. Another possibility, which is rather interesting, is having one of the neutrinos massless or nearly so, because in this case, even for normal ordering, you see here the amplitude never vanishes. There is an absolute lower bound for neutrinoless double beta decay, unfortunately too low compared with these black lines, dashed lines, which indicate experimental sensitivity of the upcoming round of experiments. So we move up to the case of inverted ordering. In this case, is much more restrictive than the generic one up there, so much so that, in fact, all of the points in this band lie inside the sensitivity of the coming experiments. So one can envisage, if this is the choice made by nature, to be able, in fact, to underpin the value of the relative Majorana phase between these two massive neutrinos. Now I turn to flavor. This is one of the sectors where the standard model fails miserably, as it lacks an organizing principles in terms of which to understand family replication, fermiomasses, and fermiomixings. And here one should appreciate the legacy of oscillations. Oscillations have demonstrated not only that leptons mix, but also that they do so rather differently from the way quarks do. You have large mixing, and this cries out for a theoretical explanation. Likewise, there is another puzzle in the family sector, flavor problem, namely the hierarchies of the charged fermiomasses. This is a very, very odd pattern indeed. These masses are not on scale, and it is very difficult to make sense of them. So nobody knows how. However, one interesting statement can be made, and that is, from the legacy of oscillation, in trying to understand the structure of the lepton mixing vis-a-vis the quark mixing, one has come about a whole bunch of new theories of flavor, here indicated in black. None of them is good enough that you can say, aha, this is the theory of flavor, but all of them are interesting. But perhaps more interesting is the fact that all of them, however different they all converge into this beautiful bottom tau flavor-dependent unification formula, which is rather successful, and I call it golden mass relation. And I believe that this golden quark-lepton mass relation does form an ingredient of an ultimate theory of flavor. On the other hand, at this point, I should also stress that perhaps the complexity of the flavor problem is so huge that we could perhaps abandon the confines of four-dimensional gauge field theory. And this is an example of warped flavor dynamics as suggested by Lisa Randall to explain the gauge hierarchy. In fact, it can be upgraded, why not, to explain all of the fermion mass hierarchies, whose explanation would be geometrized in a sense. That is far from being a practical explanation for a phenomenology, but it may be interesting for theorists. On the other hand, and more close to phenomenology, the mixing angles can be explained by family symmetries using our usual tricks, namely the imposition of a family symmetry. And it has been shown that the imposition of family symmetry is completely consistent with warping and able to give very simple analytical prediction for the mixing angles, as you see here, the tri-maximum prediction obtained from this model. And the predictions are very interesting. You see here on bottom, a very tight correlation between the magnitude of CP violation and the atmospheric octant. And on the other hand, you see here on top, the explanation for neutrinoless double beta decay will lie in these blue and red regions, and they are fully covered by the sensitivity of the upcoming round of experiments. This is for the case of warped flavodynamics with 5 dimensions. We can go 1 dimension higher to a 6-dimensional orbifold. Here everything is flat except the singular points. And in this case,
Can you conclude?
One has a unique feature of predicting the nature of the family symmetry, and that by itself predicts our beautiful golden quark mass relation. It predicts the sign of CP violation in oscillation, and it predicts the neutrinoless double beta decay amplitude. So, to make it short, extra dimension provide a very interesting framework for understanding flavor. So, since I was a bit cut in the magnitude of the talk, I will conclude mentioning that we are in a thriving moment for experimental neutrino physics, which aim to probe all the unknowns in neutrino oscillations, also many double beta decay searches, which aim to probe the Majorana nature. We have also something new, namely coherent elastic neutrino nuclear scattering has been discovered, and this provides a new probe of neutrino physics. And on the theory side, there are many items, which I list here, where neutrinos can play a key role. And these are drawbacks of particle physics to which neutrino can provide the answer. Thank you for your attention.
So I would like to ask you what will be the highlight of your talk?
Yes. Okay, first of all, I thank you again for the invitation and for the nice show the other day. I enjoy particularly music, as you said. Well, I will be talking here about entanglement and quantum correlations in particle physics, more specifically neutrino oscillations. I think this is quite interesting topic, which is rapidly growing, and I have the impression that is also a quite important topic for the community, because it helps to bring together people from particle physics with the community of quantum information. And this is very important. We are even starting to speculate that neutrinos can be used as carrier for quantum information. And you know, neutrinos have very special properties. They can go through the Earth. So maybe one day we will use this for further. But for the moment, we do calculations.
Okay, very nice. So from the little that you have seen, you have been before here, so you have a good impression, I suppose.
I have been before and I enjoyed, but this year I had the impression that something big is going on.
Yeah.
and I hope soon will be realized. So we will come to enjoy. So
you will come more often.
As I said to you, we hope to play for you here. I have done recently some study on physics with music, together with music, and I am applied this to Chopin's etudes, which we could play for you. Okay.
Excellent. And what will be your advice for the young people that we have? You have seen several young people around.
Yes.
Apparently interested in the research in our field. Do you advise them to go ahead?
I certainly advise, in general, young people from the secondary schools to go to scientific disciplines, first of all, which we are lacking. I come from south of Italy, so like Greece, we have a very similar background, I mean, and very, very, very clever young people. Second thing, those who are interested, and they should be very motivated for theoretical physics, I recommend to keep wide eyes. And this is why I think the topic I am trying to push forward is important, because of interdisciplinary in this context, of course.
I just can tell you generally what I'm going to say. This is actually, there are three parts in this talk, all related to neutrino oscillations. And we'll talk especially about the two papers which came out recently with different collaborators, and also about some earlier work we will see. Did you tell me I can go? Okay. Okay. So here are the main topics. This entanglement, which is, I will explain what I'm meaning with this term. And then more in general about quantum correlations, and especially then we will check this in the context of neutrino oscillations. Then I will mention recent work we have been doing on chiral oscillations, and then in applications of chiral oscillations, I mean, in spin-spin correlations, which is also another manifestation of entanglement. And I would like to say a few words about the neutrino oscillation formula, which is connected also with this, because this was somehow is related to the previous talks of this conference by Vitiello, and also by the previous talk about Majorana. Okay, so what I mean by entanglement in neutrino oscillations? The topic of entanglement in practical physics is it's really an important one, and is moving on very fastly, very rapidly. On one side, there is the necessity to move to bring these concepts, which are very developed. Now there is a big industry about quantum correlations in the quantum optics and the related areas, to bring this to relativistic context, and hopefully also to quantum field theory, which is not an easy task. The entanglement, we listened to a talk by Antonelli Domenico, where entanglement was a very crucial ingredient for getting information about K-short in the experiments. So it's something real, true, that we can measure. And entanglement in early works, for example, by Kaiser, the entanglement was also before acknowledged to exist in decay products. Okay, here we are talking about something slightly different. This is an intrinsic entanglement which is arising in the moment we consider neutrino mixing. Okay, and this is actually, maybe we were the first to consider this. This is an early paper we published, and then perhaps in a bit naive way we put this forward, saying that when we have such a superposition, I take the simplest case, okay, then we have done all the variations, and well, this is actually entanglement. But you know, when I was talking about this, people say, no, come on, you are wrong, because you cannot have this. This is not entanglement. This is single particle. You have Alice and Bob. They need something with what to play each other. Okay, you need two particles. Really, this is not entanglement. This is just a superposition. Observe that here is intrinsic to this notation a tensor product structure of the Hilbert space. So if you do things carefully, this is a fundamental. Well, in the same years, the mathematical, why we say this? Because I open the book and I find that when a state you cannot write in this form, in a factorized form, I find that this is an entangled state. Okay, that's the definition. Okay, for general state, they can be even, this is a convex combination of the states. Okay. Well, I was saying, in the same years, more or less, a series of beautiful papers, for example, by Van Eng, by Drowling, collaborators, etc., they actually showed that, because there was a debate also in the context of quantum optics, that these kind of states are actually entangled. The entanglement here is about field modes. It's not a matter of thinking of particles. This is a problem. If you think like particle-like, this is entangled with the vacuum, which doesn't make so much sense. And also, I learned from these papers that entanglement is a property of composite systems, and is a property, it's something that is has a relative meaning. So we have to understand what it's means. So we tried to imagine a way, according to the protocol of Vedral, how to transfer this to charged electrons. So one should do, this is a bit naive, perhaps we did this way, how to transfer this to charged electrons in order to end up with a charged electron single particle state, which, however, due to the charge and the different mass of these objects, perhaps could be spatially separated. Because the problem of, differently from the photon, the problem of neutrino is that this is intrinsic and is also not spatially separated. So it's really something very deep. It's intrinsic to the fundamental particle. So instead of having which path uncertainty, in the Vedral case, we have which flavor. But okay, we didn't do anything more on this. We have several, however, generalization essential to quantum field theory. We have done some work on this. I want to stress that this is not a partial list. There are many papers recently are appearing in which entanglement was studied in neutrino oscillations in the spirit of what we were doing initially. For example, this is very nice. They checked with experimentally the violation of Leggett-Garg inequalities. This is an analog in the time domain of the Bell inequalities of these inequalities in neutrino oscillation, proving that once more that the phenomenon is quantum. We know that this is a really quantum phenomenon, but how much quantum? We have to quantify this. And in particular, this paper took our interest, so I put a student to work on this, where they use different quantifiers of coherence. And there is this one is a bit strange, a bit complicated to understand. This is called the non-local advantage of quantum coherence. There is a hierarchy of these things. Anyway, it's related to steering. I don't want to exaggerate here because I want to tell other things, but basically the coherence in general is defined with respect, with the L1 norm to the off-diagonal elements of the density matrix. So one can define from this some quantifier. This quantifier can have a bound. When it exceeds this bound, like for Bell inequalities, you see this is, it exceeds some bound, then you say that, okay, there is a strong non-locality going on there. So what they did, let me show you the plots. They analyzed Diabaye and Minos. These are the two experiments. This is in their paper. And they found very good agreement with the violation in some regions of these quantifiers. And also they deduced that the non-local advantage of quantum coherence is the strongest one. So really here there is something very, very strongly quantum going on. What we can do with this, I don't know. This is one problem that we have now, but we want to understand. Okay, so what we did, this was the thesis of this student, the master thesis. She generalized this using wave packets, which they didn't do. And what we found, it's quite interesting, because we find that putting the wave packet information, the localization information into this, the first experiment is reproduced quite well by the Chinese group. This is a dependence on sigma. I cannot go into this. But you know, for what concerns non-local advantage of quantum coherence, we get quite different in the long distance behavior. And you see, this is in agreement, much more in agreement with the experimental points, which we don't have, however, but we have to do a fit, which tend to be up here, and they are not fitted by there. So in this case, it seems to be a much better fit by wave packets. And we observe a very interesting phenomenon. In the long distance, the non-local quantum advantage you see in the minus is violated, it's above the limit. In the case of diabase is not violated. This is very interesting. So we found that this is related to the mixing angle only. It's a function of the mixing angle, and we found a critical angle for this. This is published here. But again, we don't know now operationally what this means. It should have necessarily something to do with something you can do more in one case than in another. Clearly, the mixing angle is bigger in the case of the minus. This is the rotation, and this is Bogoliubov transformation. The key point, and this is the generator we found there, we can write in terms of this elementary algebraic object. The key point is that these two operations, two transformations, they don't commute. So Bogoliubov and Pontecorvo don't commute. If you expand this vacuum, you find the first term, which is analogous to BCS, but you see, this is different couples. So this is somehow creating some problems with Lorentz invariance. We analyzed this in another concept, but that's not the talk of today. How we calculate the oscillation formula? In Heisenberg picture, this refers to the previous talk, because sharing a picture is a bit problematic in this context, but Heisenberg picture is very fundamental, we know. If we do a nether current analysis of this simple Lagrangian with mixed mass term, we know that we don't have conserved charges, we have only overall conserved charge, global charges, and we can define the flavor charges, thank you, which are very simple in terms of the flavor fields. Okay, this is you can do it, this is classical, you can do it in 2 lines. Well, we ask now, what are the operators in which these operators here, which are time dependent, of course, the sum is conserved, are diagonal. And these are exactly the operators we have found before. So this can be checked, it's exact. Okay. So if we define our neutrino state at the reference time in the Heisenberg picture as the flavor eigenstate, as should be in the standard model, I calculate the expectation value of the charge at a later time, and I get this. So, all in terms of anti-commutators. So there is a very neat result. This is already quite old. And we have a term which is the Pontecorvo term with a Bogoliubov coefficient in front, which is almost 1, let's say. And then we get the sum. So this is like 2 harmonic oscillators, classical. You have the difference and you have the sum. Quantum mechanics gives you only the leading, the main frequency. It's correct, but it's not exact. That's it. So, and this agrees perfectly apart from chirality, because here we don't have the information about chirality. These are not chiral charges. If we put the chiral character of charge, we would get the same. This agrees with Dirac equation, of course, because the Dirac equation is correct. So okay, then yeah, there are many results, but I would stop here. Thank you very much for the attention.